Hello, students. Good afternoon. Welcome to another lecture series of Vedantu, Karnataka. This is Catherine, your physics master teacher. Can you quickly let me know if I'm audible? Let me also check. Okay. So, how are you all doing? I hope you're all doing really well. Yeah. Hi, Rakshita. Hi, Sharmila. Hi, it's Chetan. Hi, Sahana. Welcome to the class. Yes, so today we're going to finish electrostatics. We have been doing electrostatics for a while now, and today is the last and final class. Okay? So chapter 1 of your second PUC is done. Hi RXBTCC. Good afternoon. Good afternoon. Okay? So let's start with the last and final portion, which is about conductors. Are you all ready? If you all are ready, please put some fire emojis in the chat. Let's start. Okay. So as I said, today we're going to talk about conductors. Now, what are conductors? I'm sure all of you have heard the term conductors, haven't you? Yes, all of you might have definitely heard about conductors. So conductors are, things that can conduct. Conductors can be electrical as well as heat conductors can also be there. So if something conducts heat, it's called a conductor of heat. Now if something conducts electricity, you can call it a conductor of electricity. So conductor is something that allows heat or electricity to pass through. So in this chapter, we are talking about electricity. So let's forget about the heat part. So we will talk about how conductors allow electricity or electrons to pass through it. Here are some pictures of conductors. So there's gold, iron, graphite, water. All of these are different kinds of conductors. So what they do, they allow electrons to pass through it. Okay. So what do conductors do? Conductors. Oh, why is it so thick? Conductors allow electrons to pass through them. Okay. Now, how do these electrons pass through them? By applying a voltage. Okay. So whenever, imagine you have a battery and you have a full, again, let's not talk about battery because in this chapter we are talking about electrostatics. So imagine there's water. Okay. So whenever there is a voltage applied, electricity is conducted. And whenever electricity is conducted, what happens? Electrons move through it. So what can you say? You can say that all my pens are too thick today. What happened? So you can say that electrons can easily move. Electrons can easily move if a potential difference is applied and electricity is conducted. And electricity is conducted. Okay, so that is what happens in conductors. Okay. What else happening? Sharmila has fever and headache. How are you, Sharmila? Okay. Now, in this chapter, We are talking about, the chapter is about electrostatics, right? What is electrostatics? Electro is for charges and statics is for something that is at rest, that is not moving. So in this chapter, we are going to look at charges that are not moving. So we are not going to look at charges that flow through a wire, but we are going to look at charges that are not moving or charges that are static. Okay? So first we will start by looking at properties of conductors. So the properties of conductors as per NCERT, I have mentioned all the properties here for your reference. For those of you who want it as a proper note, it is here. You can just quickly take a screenshot and learn from it. Okay. Now each of these properties we will discuss in detail now. Is it clear? Are the properties clear? Let me just check. Live. Yeah, I think it's clear. Hi, Monster Gang. Okay, so let's look at each of the properties. Okay, so we will look at each of the properties here. So, number one, what is the first property? Inside a conductor, electrostatic field is zero. Okay, so that's the first property. Inside a conductor, electrostatic field is zero. So that means if you have a conductor, okay, yeah, numbers are there, so you can just refer. So if you have a conductor, inside the conductor, the electric field is zero. Now imagine you have a conductor which has there's a space in between. Here also, inside the conductor, electric field is zero. So that is the first rule of a conductor. Inside the conductor, the electric field should be zero. Okay. Now, what is, some of you might ask me, ma'am, what proof do you have? How do you know it's zero? I know it's not non-zero, so it is zero. But how do I know it's not non-zero? So let's check that. So, see, inside the conductor, for, let's say there's an electron, okay? Now, if there is an electron, what happens? There will be an electric field, there will be a force, okay? So, force and electric field will always be in opposite directions. Yes, if electric field is in this direction, the charge will apply a force on the opposite direction. So, electric field and force, there is a charge, so there's an electric field and there's a force. So, inside right now there is a charge, so there is an electric field. This is an assumption, okay? It's not really happening this way. Let's assume there is an electric charge inside the conductor. So, now there is an electric field and a force applied in the opposite direction. So, now inside, electric field is no longer zero, okay, and force is also no longer zero. So that means whenever a charge experiences a force, the charge moves, isn't it? So charge moves. Whenever a charge experiences a force, the charge moves. But we know that inside a conductor, according to electrostatics, all the charges are at rest. What is electrostatics? Charges are at rest. So, this is contradictory. Charges cannot move. So, if electric field is not zero, force is not zero and charges will move. But this does not happen. So, charges cannot move. Hence, what can we conclude? Electric field is zero. Do you understand that, students? See, but charges cannot move. But charges cannot move. So, E is not equal to 0 is wrong. Now, this explanation is for all the curious kids out there who want to know how this happens. Now, if you only want to learn inside a conductor electric field is 0, you're more than welcome to do that. For your PU exams, that's more than enough. Okay. So, you just have to learn inside a conductor electrostatic field is 0. So, because free charges rearrange themselves to cancel any electric field. So, if there are charges, they're all free charges, they rearrange, they cancel. Okay? Yes. Okay, next one. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. How do I explain that? So, for second one, Second one. So if this is a conductor, on the surface of conductor, electric field should always be perpendicular. An electric field line cannot be like this. It cannot make an angle that is other than 90 degree. Okay. So electric field should always be perpendicular to the surface. Okay. Every time it should be 90 degree. It should never be, at some angle like 60, or it cannot be like this. It cannot have angles. Okay. So that is the second point. At the surface of a charged conductor, electrostatic field must always be 0. Okay. Now, if hi KCET aspirants, welcome to the class. You all have such different YouTube names. Okay. Now, if there were any tangent components, charges would move along the surface, contradicting electrostatic equilibrium. What does that mean? See, so this is telling you, this is like a contradictory proof. Okay. Now, some of you might be wondering what happens if the electrostatic field lines are not parallel. Not perpendicular, like this. What happens in that case? So let's look at that. Okay. So these kinds of proofs are called proofs by contradiction. So you're just proving that, see, I am a teacher, so I cannot be a student. I mean, no, that's a lame con. A teacher is always a student, but let me think of an example. Okay. So it's like, you are proving something cannot be right. So the other thing is right. Okay. So you are saying you have to go somewhere. Okay. Imagine you are at a party and there's some fight happening, and then you are accused of the fight. But at the same time, you already had left the party. You were home at the same time. So you can prove that I was home, so I cannot be the culprit at the party. Right, because I was home. So if you prove that you are home, that means you are not the culprit. Same thing. So we are proving that electric field lines cannot form an angle. It is always perpendicular. So it is a proof that electric fields have to be perpendicular. Okay, so we are just proving the contradictory is wrong. Okay, so this is proof by. Can you hear a dog bark? I can hear a dog bark. I don't know if that audio is coming to you, but if it's coming, I'm really sorry. There's a dog barking somewhere. I'm at home. So, yeah. Proof by contradictory method. Okay. See, can you hear the dog? Can you let me know in the chat if you can hear the dog? I'm really, really sorry, students, that if it's disturbing you. So let's say the electric field is at an angle. Okay, it's not at 90 degree. If the electric field is at an angle, then how do you resolve it? Then you resolve it by, hello Chaitra. Then you resolve it by taking a horizontal component and a vertical component. Okay. So when you resolve it by taking a horizontal component and a vertical component, you will get a force. So if this is the direction of electric field, then this is the direction of force. So there will be a force. If there is a force, what happens? The charges are moving. So the charges shouldn't move. The charges shouldn't be moving. This is parallel, this is perpendicular. The charges shouldn't be moving. If the charges are moving, then it's not electrostatics. Charges are static in electrostatics. So only perpendicular component should exist. Okay, so if the perpendicular component exists, then what happens? Then even if the force is in this direction, it is just pushing the charges to the boundary. It cannot move further than that. Okay, so that is why it is always perpendicular. Okay, so electric field lines are always perpendicular or normal to the surface. Okay, let's look at the next one. Next one says that the interior of a conductor has zero electrostatic potential. Okay, the interior of a conductor has zero electrostatic potential. So if you take a conductor, okay, inside the conductor, we already know that electric field is zero. Yes, we know that. Now, the charges always lie on the surface of the conductor. Okay, charges are always on the surface of the conductor. Inside the conductor, it is zero, the electric field lines. Now, let's apply the law that we've already learned. E dot dA is equal to Q by epsilon naught. Now, from this, we know that electric field is zero. So, if electric field is zero, 0 dot dA is zero. So, Q by epsilon 0 should also be 0. So, shouldn't Q be equal to 0? Yes, isn't it? So, if Q is equal to 0, that means inside there is no charge. Okay, so there is no charge. So, if there is no charge, there is no electrostatic potential. So, this law can also be said that the interior of a conductor has no excess charge. Has no excess charge in static condition. Okay, the interior of a conductor has zero electrostatic potential, or you can say the interior of conductor has no excess charge. So how did we prove that? Very simple. Inside the conductor there is no electric field. If electric field is zero, charge should also be zero. So we can say it has no charge. Okay, is this clear to all of you? Okay, now let's move on to the next property. Next property is that electrostatic potential is constant throughout the volume of the conductor that has same value as on its surface. Okay, so this just says that, okay, for this it's very easy. What we can do is we can use this law. So electrostatic potential and electric field. So electric field is equal to minus dV by dr. We've derived this formula in the previous class. So inside a conductor, okay, inside a conductor, what is electric field? Electric field is zero. Yes. So inside a conductor, electric field is zero. If electric field is zero, what does that mean? That means minus dV by dr is equal to 0. Now, when you differentiate, what do you get? 0. Differential of something is 0. Now, what is that something? Yes, the differential of a constant is 0. So, from this, we can prove that V should be a constant. Why should V be a constant? Because its differential should be 0. Its derivative should be 0. Its derivative is 0 because electric field is 0 inside a conductor. So, this means that V is constant. So, now we get that. So now what we get is, So now we get that if you have a conductor, inside the conductor, voltage is a constant. That is because electric field inside is 0. Is that clear to you? Yes. So that is the next rule. It's very easy. E is equal to minus dV by dr. So inside the conductor, E is equal to 0. So if E is equal to 0, minus dV by dr should be a constant. Okay? Yes. Is this point clear to all of you? Now some of you might be wondering, ma'am, where did you get E is equal to minus dV by dr? I've already derived it in my previous lecture. Okay? I think part 4 or part 5, you can just check that out. Yes? So if students, I recommend watching the series in order, okay, because it's all one after the other. Okay, next question. Sorry, next property. Electric charges on the outer surface of a conductor. Charges reside only on the outer surface of the conductor. Okay, I read it wrong. Charges reside only on the outer surface of the conductor. This is also something that we've been discussing. So there are no charges inside, charges are only outside. Okay, now let me just give you a small proof for that as well. Okay. This is point number 5. Okay. Point number 5. What was the point? Electric field at the surface of a charged conductor. Okay. So let's say there's a conductor. Okay, let's say there's a conductor that looks something like this. So this conductor obeys a rule. Okay, what is the rule? The rule is that sigma is proportional to 1 by r. Now what is sigma? What is r? Sigma is the surface charge density and r is the radius of curvature. Okay, so sigma is the surface charge density, r is the radius of curvature. So let's say there are field lines. Okay, now if you have a charge here, now this is the radius of curvature. So it's a small radius, this is a big radius. See, what is radius of curvature? It is the, if it's a spherical surface, the radius of the spherical surface. So here, if I take this as A and this as B, obviously B has a bigger radius of curvature, A has a smaller radius of curvature. Yes? Okay. Now, if I have a charge here, I'll have some electric field lines here. Here also I have some electric field lines, but my electric field lines would be stronger at A and weaker at B. Why? Because of this particular relationship. So according to the relationship, the surface charge density, which is the number of charges or the number of field lines, is inversely proportional to the radius. So if the radius is small, lots of charges. And if the radius is big, the charges are very small. So that is how electric fields vary on the surface of a charged conductor. Okay. So here, electric fields on the surface of a charged conductor can be given as, how can I say that? Okay, so if these are the electric fields, okay, if these are the electric field lines, okay, from A the electric field lines are going out, then I can say that the electric field lines at the surface will be equal to sigma by epsilon naught. How can I say that? Sigma is charge. This is basically charge. Okay. Sigma by epsilon naught. So E is 0. Inside. Okay. So the electric field lines, we have to prove that electric field lines are only on the surface. So how it varies on the surface, I already said. A smaller radius of curvature will have lots of charges or lots of fields. A bigger radius of curvature will have few fields. Now, if you look at the surface, on the surface, electric field lines have the relationship sigma by epsilon naught. Inside it's 0. So obviously charges have to be on the surface. That's why there is an electric field on the surface. Now, how the sigma by epsilon naught came? The derivation I've done in the last class. Now, students, if you have a sheet or if you have something where there are fields in 2 directions, then this electric field becomes sigma by 2 epsilon naught. Okay? So, if it's the field is only in one direction, it is sigma by epsilon naught. If the field is in two directions, then it becomes sigma by 2 epsilon naught. Okay. So for electric field is only electric charges reside on the surface of a conductor, or electric field is only at the surface. These are the two things that you need to know. Depending on the curvature, the number of field lines or the surface charge density will change. And on the surface, there is a field which is sigma by epsilon naught. Inside, the field is 0. Is that clear? Yes. Sorry. Okay. Yeah. That is the next point as well. I explained that also. So the electric field outside a conductor is perpendicular. It is E is equal to sigma by epsilon. In some cases, it becomes sigma by 2 epsilon naught, which also we've discussed in the last class. That is for, I can give you the example for the sheet. So when you have a sheet, what happens when you have a sheet of charge? Electric field flows in both directions. So in that case, you will have sigma by 2 epsilon naught. Okay? Okay. Now let's look at how two conductors can be connected. Okay. So let's do that here. Okay. If you have one conductor here, another conductor here, okay. If this conductor is at a high potential and this conductor is at a low potential, what happens? Charges flow from high potential to low potential. Okay. So when two conductors are connected, charges flow from high potential to low potential. Okay. So when there are two conductors, charges flow from high potential to low potential. Now in the same case, imagine I have two conductors that have the same potential. Okay. So this is V1 and this is V2. If they have the same potential, then there is no flow of charge. No flow of charge. Now this is also called as the equilibrium condition. Okay. It's called the equilibrium condition. When you have two conductors and there is no flow of charge between the conductors, then it's called equilibrium condition. Now sometimes you can create this equilibrium condition by just connecting a conductor to the ground. Okay. So this is called earthing. Okay. So what is earthing or grounding? It also can be called as grounding as well. So that is when you have a conductor, it will have some charges, you connect it to the earth. So what happens? All of the charges from the conductor, they flow to the earth. Okay. So when all of the charges flow to the earth, that is called earthing. So this is mainly done in your homes and all. If you have your power supply, your socket, always one wire of the socket is going to be connected to the earth. So that is because if there is a leakage of, if there is extra charges, these don't come out. You don't get a shock. They all go to the earth. See, if you have these electric wires, the wires, these wires that you have, I don't know how to draw them, are electrical wires that we have outside on the roads. Okay. So if there's a bird sitting on one wire, it doesn't get a shock because that one wire, it has a fixed potential. It doesn't flow anywhere. Okay. But if the bird keeps two legs on one leg on one wire and the other leg on the other wire, what happens? If one wire is at a higher potential and the other wire is at a lower potential, current flows through the bird. What happens? The first case, the two wires are two conductors. So from high potential, it flows through potential. It flows to the wire of low potential through the bird. So when it flows through the bird dies. The bird just becomes a grill. Okay. So that happens. Now, even if you go touch one wire alone, If you're touching the earth, if you're standing on the ground and touching one wire, you will die. Okay, don't do that. Why? Because what happens? From the wire, now charges can flow through you to the earth because earth is a conductor. In the case of the bird is in air. That's why there's nowhere for the charge to flow. But if you're holding one wire and touching on the ground, it will flow through you to the earth. And if you're holding two wires, from one wire to the other, it will flow through you. So those are all very dangerous things. These are three ways in which conductors can be connected. Okay. Now we will see how conductors behave with cavities. Okay. So let's look at that. Let's look at how conductors behave in cavities. Oh my god. Okay, thank you, Chaitra. It's clear. Yeah. Okay, now if you have cavities, let's take green. Conductors with cavity. How it behaves is what I will explain next. Now imagine there is a conductor. Okay, so there's a conductor. Okay, there's a conductor, and this conductor has no charges inside it. Okay, here it has no charge. So the charges are all on the surface of the conductor. Yes. So this is how usually a conductor is. A conductor will have charges at surface. It will always have charges. It will have charges at the surface and no charges inside. So this is how generally a conductor is going to be. It's going to have charges on the surface, no charges inside. Now, imagine I have a charge inside. Okay. So what I'm going to do is, I'm going to take the conductor. Okay. And I'm going to put a charge inside. Let's say I put a charge inside. Now what happens? Outside there are lots of charges. So from outside what happens? All the negative charges are attracted here. So there will be a lot of negative charges here now. So from the surface all the negative charges will be attracted towards the center because inside in the cavity I place a positive charge. Now on the surface what will remain? You will have positive charges. On the surface there will be positive charges. On the surface there will be positive charges. Inside there will be negative charges. Okay. So these negative charges are called induced charges. These negative charges are called induced charges because these are charges that are induced because there is an extra positive charge in the cavity. Generally there is no charge in the cavity, but because there is an extra positive charge in the cavity, these are induced. Okay. Yeah. Now I can consider another case where I have cavity. Similar thing, I have a cavity, but this time let's say I have no charges inside the cavity, but I have a charge outside. Let's look at that case also. Let's look at the case where inside there are no charges, but outside here I have a positive charge. So now what happens? On the conductor, the charges rearrange and all the negative charges come to this side. Positive charges stay on the other side. This happens because there is an extra positive charge. Yes. So all the negative charges, they flow to this side. So this is how charges flow inside a conductor when there is a cavity or when there is an external charge somewhere else. Do you understand that? Now, you can use a similar phenomena to explain something called as electrostatic shielding. I'm sure all of you have heard that one term in class. So, what is it called? I will explain that. Electrostatic shielding. So, this is basically shielding from charges. So, when you're driving a car, even if there's thunderstorm, you are protected. See, the thunder is not the thunder or lightning or the charges are not going to strike the car and then burn you inside. They're just going to strike the car and they'll be flowing through the surface of the car. They'll be going to the ground. It is like you are inside a protected, structure. It's like a chamber where how many ever charges hit the chamber, it does not pass through the chamber. They just flow over the chamber, but they don't affect anything inside the chamber. So that protection is called electrostatic shielding. So now how does electrostatic shielding takes place is what we will draw. So let's say this is a conductor. Okay. Imagine this is your car and this hole inside is the inside part of your car and you're sitting inside the car. So inside there shouldn't be an electric field because you're sitting inside the car. So inside there is no electric field. Outside there are charges. Okay. Outside there are a lot of charges. Now a lightning comes and strikes. So let's represent the lightning by a negative charge. So this negative charge is coming and going to hit the conductor. Okay. So this negative charge comes. What happens? Whenever this negative charge comes close on the conductor, what happens? A sudden redistribution of charges happen and all the positive charges come close and the negative charges go to the other side. This is a very quick process. Okay, all the positive charges come this side, negative charges come this side. So now what happens? From the positive, the electric field lines go like this, okay, to the negative. Now from the negative, to the negative also electric field lines come. But none of the field lines are entering the conductor. All of the field lines are outside. Now because of the positive charge, there are field lines. Because of the negative charge, there are field lines. But none of these field lines enter. These field lines stay on the surface. So it's like a shielding. It's like a protection. So whatever is inside, it's always going to be protected. Okay. So this process is called as electrostatic shielding. Is this clear? When there is a charge coming. So this could be a very good example I can give you is a car and lightning coming in. So this negative charge is lightning. So all of these electric fields are on the surface of the car. They don't enter inside the car and through the car tires they can be sent to the earth. So it is not going to affect anything. So you don't get affected by lightning when you're driving. But if you're simply standing, okay, on a ground, okay. So let's say this is you. This is just additional information. So this is you and you are standing on a ground. So now what happens? There is an electron filled cloud. Okay. And this cloud wants to discharge. It wants to send out its charge to the earth. So it will try to capture the closest conductor, the closest object that can carry charge. So if you are standing there, this cloud will capture you and it will transfer all the charges to you and you will get a shock. Now, if you are not there, it has to go for the next conductor. And so that's how if you're simply standing outside when it is raining and when there's heavy thunderstorm or lightning, you might get a shock or it could be very dangerous. Okay, don't do that. So the same thing applies for these lightning protection devices. Have you seen that? So those are poles on building tops. So on top of buildings, there are thin, long poles. So the advantage of that pole is whenever this cloud feels like it wants to discharge and it looks for a conductor, there's already a conductor which is at a very high position, which is the lightning detector. So all of the charges go into the lightning detector. It is directly connected to the earth, so it just goes into the ground. No harm to the building. So it's like it's killing itself to protect the building. It doesn't die. It just allows all the current, all the charges to pass through it and passes it to the ground, protecting the building. So if this lightning detector, you are just like this lightning detector. When you are on a playing field, you are in lightning. You are doing the purpose of the lightning detector. So don't do that. Okay. Yeah. Because see, the lightning detector, it can keep doing it. It's not going to die. But if you go stand on a field with lightning, you will get charges and it will affect you. Okay. So that's all about conductors that we need to learn in this chapter. Okay, is that clear? Hi Praveen, how are you? Sharmila, my bande. Okay, okay. Now, since we discussed so much about conductors, now let's talk about dielectrics. Okay? Hello Praveen. Long time. Okay? So now let's talk about dielectrics. Okay. So for dielectrics, first let's talk about a dielectric material. So a dielectric material is any material like wood, glass, air, any material. Okay? So this is just a material. Okay? This is a material. And let's say you're passing an electric field through this material. Okay? You're passing an electric field through this material. So I will call this the external field E naught. Now, whenever an electric field is passing through a dielectric material, the material induces an electric field within itself. Okay? So now there is an electric field induced in it. So this is called E induced. Okay? So this induced electric field is because of the polarization of the medium. So it's a property of the medium. Okay? This electric field induced is due to the polarization of the medium. Okay? So think of a dielectric. It's simply a medium, wood, glass, air, whatever, any medium. You apply an external electric field. Because of the external electric field, it produces an internal induced electric field in the opposite direction. And that internal induced electric field is due to the polarization of the medium. So the net electric field, what will the net electric field be? The net electric field is going to be the resultant, E naught minus E induced. It's going to be the resultant electric field. So it will always be less than the external electric field, and this is going to be less than the external electric field, isn't it? If E naught is a very high value, some of it is cancelled out by the induced electric field. So the output, the net electric field will definitely be less than the external electric field. So this property is experienced by materials called dielectric. So dielectric materials are materials that are not conductors. They are not conductors like water, wood and all of that. They are not conductors and they weaken the field that passes through them. So what do they do? Even if you take a block of wood, even if you pass an external field through it, the wood produces an internal field in the opposite direction. It cancels it out. So a very small amount of field comes out. So that is a dielectric. Okay. Dielectric. So a dielectric is non-conducting. A dielectric is non-conducting and weakens the field. Okay. Now, so what will the net electric field value be? So E net will be equal to E naught is bigger. So E naught minus E induced. Okay. So from this we can say that E net can be equal to E naught by a constant called K. Okay. So this is a new relationship that you will learn here. E net is equal to E naught by K. Now this K is not Coulomb's constant. It is not 1 by 4 pi epsilon naught. What is this K? This K stands for dielectric. Sometimes, when I write it, I miss alphabets. Okay. It's not because I don't know the spelling. It's because when I write it, I think that I've written it, but sometimes I just miss the alphabet. Dielectric constant of the medium. Okay. And this keeps changing depending on the medium. So for each medium, it is how the induced field is there and all that, how polarization takes place. It keeps changing from medium to medium. Now, okay, so from this, let's do some math. Now, if so K can have different values. Let's look at that also. So let's say K for a ceramic plate. Okay. K for a ceramic plate, let's say it's like 300. Okay. Any value from 200 to 400, let's say it's approximately 300. So K for air, it could be approximately 1. Okay. Now, K for metals is approximately infinity. So what does this mean? This means that, so for ceramics it's 300, so it produces that much induced field and it does not allow that much to pass through. Metals is infinity, so for metals external will be more, it will allow them to pass through. So dielectrics are usually not conducting elements, so it will have different values. So K will have different values depending on what the material is. Okay, now let's just do some math. So if E induced is E naught minus E net. Okay, and we also know that E net is equal to E naught by K. So now what I will do is I will substitute E net. So now my next formula will be E induced is equal to E naught minus E naught by K. So this will be, I'll take E naught outside, 1 minus 1 by K. So now I have a formula to find out my induced field. So E induced will be E naught into 1 minus 1 by K. Now, so imagine the question is, the external electric field is given to you. The dielectric constant K is given. So identify how much electric field the dielectric material induces. So in that case, you can just use this formula. E induced is equal to E naught into 1 minus 1 by K. Okay, so it depends on material. So imagine there's a block of wood and imagine there's an electric field of some 10 passing through it, and let's say the constant is 5. So you can find out E induced by simply substituting E naught and K. If you have E induced and E external, then you can find out the net electric field. But sometimes you don't have the net electric field. You only know how much you are inducing and you know the dielectric constant of the material. So in such cases, you have to use this formula. E induced is equal to E naught 1 minus 1 by K. Is this clear to all of you? Yes. Can you quickly let me know in the chats if this is clear? Yes, no. Let me see what's happening in the chat. Okay. Students, when is did you all get your first unit test dates for physics? Yes. We'll prepare for first unit test together. Did you all get your dates? Okay. Is this clear to all of you on dielectrics? Any doubts? Harshita, it's Chetan, Sharmila. Who else is there in class? I cannot see the rest of the people. So all of you, please do like the video and subscribe to the channel. Also share it with all your friends. Okay. So we need people in the channel. Only then we can keep the channel running. So please do share the channel to all your friends. Ask them to subscribe and ask them to like all the videos. Ask them to watch the videos and learn from us. Okay. So we grow as a family. Okay. Next I will write down a relationship between dielectrics and epsilon naught. Okay. So let's relate what should I relate? E and E naught. Okay. So we already know the relationship. So E stands for E net. E is equal to E naught by K. I already know that. Now I know that the external field that I apply, it always obeys Coulomb's law. Yes? Now before that, let me explain what the scenario is here. So imagine you have a charge Q. Okay? You have a charge Q and it is at a distance R. So there is an electric field here, E naught. But this charge has to pass through a dielectric medium. Okay, so whatever we learned in this first chapter at the beginning, same thing I do, but in here I insert a dielectric medium. So I keep the charge and I look at the dielectric medium so I look at the electric field after the dielectric medium. Okay, so I have a charge, I have a dielectric medium, I look at the electric field after the dielectric medium. So now the dielectric medium will also produce an electric field. Okay, a weak electric field it produces. So this E naught is basically from Coulomb's law. I know that it is 1 by 4 pi epsilon naught. Q is the charge, R is the distance into 1 by K. Okay. So this we know. Now let's continue. Now what I'm going to do is I'm just going to replace the positions of epsilon naught and K. You will see why I'm doing it. So this is equal to 1 by 4 pi epsilon naught, so K I'll put it here, K into Q by R. Okay. Now epsilon naught K, I can write it as epsilon M. What is that? Epsilon naught K, I will write it as epsilon M. So this is basically the dielectric. Okay, epsilon M is called permittivity of the medium. Okay, it's called permittivity of the medium. And in this case here, they have values. What is the value of epsilon naught? I'm sure it's, you're all by hearted it now. 8.85 into 10 raised to minus 12. And what is K? K is dielectric constant. Okay, so K is the dielectric constant, epsilon naught is 8.85 into 10 raised to minus 12. Epsilon M stands for permittivity of the medium. Now I can modify my equation. Now what is my final equation? My final equation is, which color should I put? Orange. Okay. My final equation is E is equal to 1 by 4 pi. Instead of epsilon naught K, I will write it as epsilon M Q by R. So this is my new equation for electric field. So this is the equation for electric field of a medium which has a dielectric in it. Okay, so whenever there's a dielectric, what is actually happening to the electric field? The electric field reduces by a factor K. Okay, you can see that. See, E naught is the initial electric field. E naught is the initial electric field passing through a medium, any medium. Now, passing through any medium. Now, if I put a dielectric in between, it is divided by the dielectric constant K. Okay. Okay, wait. No, ma'am, you didn't get the timetable. Sorry, what are you doing here? Ma'am, what is the value? Ma'am, how is that K value is derivative or universal? K value is not 8.85 into 10 raised to minus 12 here. The value of epsilon naught is 8.85 into 10 raised to minus 12. So your doubt is if it's universal, right? The value of K, it depends on the dielectric medium. Okay, so the value of K keeps changing. So if the medium is wood, it will have one value. If the medium is air, it will have another value. If the medium is something else, it will have some other value. Okay, so yeah. Yeah, epsilon naught is a universal constant. It's always a constant. It's 8.85 into 10 raised to minus 12. It's never going to change. Is that clear, Praveen? Yeah, epsilon. Yes, yes. I hope that's clear. I've explained epsilon. Okay, so this is the relationship between epsilon, E and E naught with respect to epsilon. Okay. Okay. So that is there. And then we also looked at, what happens when you induce a dielectric. So this concept is very important, students. When you insert a dielectric, what is happening to the field? So the total external field is reducing. So now you know why, some are not conductors. Even though you pass a field, some materials, they don't conduct. That's because they produce an induced field in the opposite direction, which cancels out some of the external field. Okay. We also looked at the different what happens when conductors have cavities. So when there is no charge in the cavity, what happens? The charges lie on the surface. There is no charge inside. A perfectly normal conductor. Now, if there is a charge inside in the cavity, so if there's a charge inside in the cavity, what happens? Then all the negative charges come close. So there are induced charges around the cavity now, which is usually not there. So in a conductor, usually inside the conductor, nowhere there is charge. But when you bring a positive charge inside the conductor also there are some charges. Now on the surface of the conductor also you will have some charges. Now inside if there is no charge but outside there is a charge, what happens? Suddenly charges redistribute. If this is a positive charge, all the negatives go here, positives go here. So there is a redistribution of charges. Okay. Now, the same principle applies for electrostatic shielding as well. So, electrostatic shielding is when you are protected. So, it's like you are in a cage and whatever lightning or whatever electrostatic rays, when it hits the cage, it flows through the surface of the cage. But it does not pass through the cage. Even in this case, you can see there are positive and electric charges. They're all flowing through the surface of the cage. But they're not passing through the cage. Okay? And we also looked at the different properties of conductors. So what are the different properties? So inside the conductor, all the electric fields, all the charges, there are no charges. So electric field is 0. And on the surface of the conductor, you can see electric field lines are always perpendicular. Yes, electric field lines are always perpendicular. And inside, since there are no electric fields, the potential is also 0. Okay, so it acts like a equipotential surface. There's no potential, it's all the same. All right. And what else? Electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. How did we prove that? We just used the formula E is equal to minus dV by dr. This formula I've explained it in the last class. So E is equal to minus dV by dr. So what happens? If E is 0, we know that E is 0. Inside a conductor, it's 0. Electric field is 0. So if E is 0, then what happens? dV by dr should be 0. Now, differential first PU portion. If you don't know that, you can watch first PU videos also. So, dV by dr should be a 0 only if V is a constant. Next point is charges reside only on the outer surface of a conductor. And on the outer surface, charges are given by sigma by epsilon naught. Okay. Okay. Chetan got 96.73 in 10th grade. Wow. Congratulations, Chetan. Okay. Yes. So students, even though you're all, talking in the chat, please make sure you follow the lesson. You might be comfortable watching the lesson at a 2x speed so you can get it fast. That's all up to you, but please follow it. Okay, so for your first unit test, you will have these 4 chapters, the first 4 chapters, out of which the first chapter is done now. Okay. Yes, so we are completely done with electrostatics. Numericals on electrostatics, a video will be there. I don't know if I'll be doing or somebody else will be doing it, but it'll be definitely there on the channel. For your first assessment, you will need numericals as well, right? Okay, so students, I hope you all enjoyed the session. Electrostatics is done, so I will be starting the next chapter next week. Okay, is that clear to all of you? Anything you want to ask? Okay, you're all waiting for each other. How do you know each other? So do you all, take your chats and go to instant chat or something? It's surprising on how you people connect with each other. Okay, so yeah, bye bye, bye Praveen. I'll see you all in the next class with the next chapter. So by then I want you to follow all the lectures. So we did this class in 6 parts. So all 6 parts you should watch clearly and understand the concept. So if you are preparing for competitive exams, you shouldn't just by heart the derivations. You should understand the concepts as well. But if you just, trying to appear for your PU, then you can by heart the concepts. But I still don't recommend it. I want you to understand the concepts. Okay? Okay. Okay, students, bye bye. I'll see you in another class, another video. Let me know how the class was in the comments.